So today topic of discussion is inference graph, and this is a solution where we have more than one ML services to be deployed and maintained. Let me set the context right. So this is a ML pipeline, it's a common ML pipeline which we use for ML service, right, which has two phases, a training phase and a prediction phase. And training phase is generally an offline phase, and the output of this phase is generally a ML model artifact. Right? And this is where a ML engineer comes into play, where they want to take the ML model and do a scale development. Quite often, the case is we have to deploy this model in a real-time case. So we have a REST API endpoint which is exposed to the client. We come with the request, and it's processed by the ML model and we return a response. It's a typical ML pipeline. So when will be the life of ML engineering easier? When there's only one ML service backing a use case, right? But generally, that's not the case. So we expect to have only one ML service, but generally we end up for solving a use case more than one ML services. Then we have an array of ML services which has to be tied in a particular fashion, probably in a form of a graph, and to get a particular output. Right? Today, the objective of our talk is to give you a solution to handle such complexities. With that, let us introduce ourselves. I am Sharlesh Nivasan. I am working for PayPal. I have been working in big data engineering, data science, and ML space for around 8+ years now. And I've been working in for a variety of companies, starting from startups, mid-range companies, and also tech giants like Ericsson and PayPal. And with that introduction, I'll ask Saurabh to introduce himself.
Hi everyone, I'm Saurabh. I work at PayPal as a ML engineer, where my primary responsibility is to take the models from development phase to the deployment phase to the production phase. And then, so I want this process to be more robust, more trackable, and that's where our efforts come into picture. These days, my areas of research is also in the side where how can we reduce the inference time of machine learning models, especially the large language models, how can we reduce the inference time? Because that directly results in the amount of cost, the cost that we're going to save for the infrastructure. So if any of you has to share information on that, please do that. And I'm 7.5 years old in this industry and has played multiple hats of being a developer, being a data engineer, being an ML engineer, and responsible for building platforms. Thank you.
Thanks, sir. Okay. With that, let's go to the agenda. So I'll introduce quickly to PayPal and specifically customer success platform which we represent, and I'll also talk about how to use ML in customer success platform. After I quickly introduce chatbot, which is the bread and butter of any customer success platform, I'll also introduce a series of ML services which back our chatbot, and then we'll specifically talk about one scenario, and we'll take this scenario to represent how the power of inference graph. Then I invite Saurav to help us walk through the technical details of inference graph along with the demo, and he'll wrap the session with the value addition, which we got from inference graph. Right? Then we'll wrap the session with key takeaways. With that, so let me quickly go through what we do in PayPal. So most of you are aware of PayPal, so we are the leaders in financial services, and our mission is to democratize financial services. So what do we mean by democratize? It's to bring financial services to common man, make it more affordable, easily accessible, irrespective of their background, be it the country of origin, be it their financial background, right? And now to talk about what is the golden circle, why we do what we do in customer success platform, is we understand that every customer, every PayPal customer deserves a world-class customer service. Right? So we try to achieve it using our state-of-art cutting-edge technologies, in this case it's ML. And as well as we have been a customer champion for around 2 decades now, and we aspire to continue to do so. But having said that, let me introduce you to the ML stack. So we majorly play in two major ML areas. One is the natural language processing, and other is the computer vision. So why natural language processing? As we can expect, most of our conversation with customer happens through text, right? So be it emails or be it chatbots, messaging, social media, so it's almost text. So that's why one of the strong areas is NLP systems. And few of the areas which we cover in NLP systems are summarization, translation, deduction, speech to text, to name a few. And the next other area is computer vision, where we have a bunch of documents to be processed, and the main objective here is to extract content from the document and understand the context of the document itself. Right? Having said that, though I've quite mentioned that we use state-of-art and cutting-edge technologies, ML stack. But our day-to-day decision is always customer-centric, it is always driven by business KPIs. Two main aims of business KPI is one is customer value addition, and other one is reducing the operational cost. I mentioned few of the business KPIs here, four of them, but actually in day-to-day reality, we are actually driven by more than 10 business KPIs. Let's talk about few of these business KPIs to drive home the point. Let's talk about what is contact deflection percentage. So this is where we provide customers with self-help tools like knowledge base or chatbot or FAQs, etc., so that they can solve the problem for themselves instead of waiting for an agent to get aligned. Right? But in an unfortunate situation where they are not able to solve the problem by themselves, then of course they are going to reach out to us and we are going to align a human agent to help them. Right? In that case, the next business KPI kicks in, which is average speed of answer. Because the customer is going to wait in a queue, so we want to intelligently route the customers who are waiting on the queue to the agents, so that the average waiting time on the queue is reduced. Right? Again, once they are getting assigned to agent and there's interaction started between agent and the customer, now we wanted to equip agents with certain tools or certain features so that they can quickly answer the problem of the customer. Okay? That is where the next business KPI, which is average handling time, kicks in. Okay? The next one is we don't want our customer to come back to us with the same problem again and again, so we wanted to solve at the first go, where first alignment with the customer, we want to solve their problem. That's where the first call resolution rate comes into picture. So these are the few KPIs which drive the decisions which we take daily. Having said that, let me introduce you to the chatbot paper. It's paper assistant. If you happen to reach to the customer support portal of PayPal, you will see this PayPal assistant chatbot. As you can expect, this is an automated, fully powerful chatbot, and this is not backed by any human agent. Right? So to make this chatbot fully autonomous and powerful, it should be, of course, backed by a bunch of ML services, mainly energy services. Right? So I put here a few of the ML services, but it is again it's not limited to just this 6 ML services, it's actually backed by more than a dozen ML services in reality. Having said that, today for bringing the power of inference graph, let's narrow down into a single scenario. That is nothing but transfer of session. So let's understand what is actually transfer of session in the chatbot context. Right? So say a customer is coming to the chatbot and he is typing a query. And for some reason, unfortunate reason, the bot is not able to address the customer's query. So what happens? The actual session, the conversation with the customer gets transferred to a human agent. So this is a candidate for a transfer of session. And this is not only the case; there are other cases as well. For example, agent is interacting with the customer and he is asked a question, but customer took more than 24 hours to get back with an answer. Right? So in that case, a new agent will be aligned. So in this case, this is a transfer of session between agent to agent. Okay? Again, there can also be a case where agent is trying to help the customer, and for some reason they fit to take it over a call. So they moved from a chat channel to a call channel, right? And they discussed few things, and then they came back to chat to grab the conversation. So there is a shift in the channels, right? So this is also a candidate for transfer of sessions. So, but what is the bottom line whenever there is a transfer of session happening is every time there is a new agent getting aligned, right? So, if I am the agent getting aligned, what I have to do? I have to go through the complete conversation, what happened just before I got aligned with the customer to get the context, right? Which is going to directly affect the average handling time. Right? So, so how can we help the agent to solve this problem? Can we give them a quick summary of what happened till now in 1 or 2 lines? Also highlight why the customer has reached us, and also derive few entities or details which the customer has already provided to us. Right? If you can provide this information upfront to the agent, it will be really helpful for us. Right? That is what we are trying to achieve. So let's take a quick example. So in this case, in this conversation, the customer has reached the chatbot. They wanted to have some transaction detail about a transaction that happened on a particular date for a $50 transaction. Right? And also the customer wanted to cancel that transaction, right? But for some reason bot was not able to help, and the bot found it fit to add a new human agent, right? Also the meantime, the main reason why the customer is coming to us is the transaction inquiry and also the cancel payment. Also, the customer has already shared few details with us in the bot, namely the transaction date and the transaction ID and also the transaction amount, right? So we are going to try to give these three main values to the new agent: summary, 2 to 3 line summary, and main highlight intents, and also few entities or the details which is already shared to us by the customer. Right? So from this point, how the agent can react? Either the agent already knows what's the problem, so once they get connected to the customer, they already have a solution. Or the agent can also go ahead and ask the missing pieces of information and then quickly answer the customer. Right? Having said this example, let's also see what are the different ML services which is going behind the scenes to achieve this. Right? So this is the ML pipeline which is generally used to solve this problem. Here, the raw text means all the conversation that happened in the session just before this session started. And what we are trying to give is a summary of the conversation and the highlight intents and entities. Right? As you can expect, all these three are parallel services, parallel intent, summary, and entity services. And we also optionally are tied up with language detection and translation. Why? Because most probably the customer is having the conversation in their native language, right? So then what we do, we transfer it into our de facto language, we translate it into a de facto language which is English, and then we get the summary intent and entity. At this point, it's up to the agent whether they want to read the content in English or they want to again customize it to their own language, right? Having said this, I'm going to pause here and now I'm going to call Saurav to help us know the technical details of how an inference graph is going to be used to solve this scenario. Right? Over to you.
Okay, hi everyone. So, Shami will explain the business relevance of this scenario. Now let me take you to the let me help you understand how to actually build this system. So, the idea is that all of these services would be running, and there will be some relationship between these services. And when a request comes to the front-facing service, then as per the relationship, the traffic has to be routed accordingly, and finally you should get an output that should contain the summarized text, the intents, the entities, and all the important pieces of information from the raw text. So, let's try to understand briefly what exactly do we mean by inference graph. It's pretty simple. It's just a bunch of ML services, ML models working together, and they have connections between them, they have relationships between them. And we can map this information in a form of graph. Just like in if you're familiar with Apache Airflow, there's a DAG there, or in Spark, Apache Spark, there's a DAG there. Similarly, it's also a DAG where the information flows unidirectionally from the front-facing system to the final piece. Multiple models acting as a node, and their relationships are managed as edges. Let's also try to understand a couple of standard use cases where we can really build inference graph for. Let me tell you before that, in the entire MLOps cycle, we are targeting the deployment and serving part of MLOps. So if you want to know precisely which area of MLOps we are talking about today, it's mostly towards the deployment, towards the serving part. Because as an MLOps engineer, we want to make our lives easier when it comes to the deployment. There has to be standardization, there has to be, our life should be easier when we, and by bringing such design patterns into our system. Okay, so coming on to one of the use cases such as model chaining, an inference graph can very well be used there. The idea is very simple, multiple models are acting in conjunction, and the output of one model goes as an input to another model. Real life use case would be the optical character recognition problem, where given an input image, we want to extract the text out of it. The image has to go to first model where, let's say, the rotation problem of the image would be corrected, the blurriness of the image would be corrected, and that output will go to model B, which all it does is just finds the regions, the contours where the important piece of information is there in the image. Then that signal can go to the model C, where actually extract the text out of the image, and from that text, we can extract important pieces of information. So model chaining is one use case where inference graphs can be used. Another is ensemble, where we simply want the output to be a combination of multiple inputs, maybe a weighted average of the outputs coming from different models. Maybe we want to have our own logic of combining the outputs from multiple models into a single output. So there also you can use inference graph. A very well use case could be the text processing and analytics use case that we are speaking today. You will find this design pattern in our demo as well. Next could be the scenario where you want to route the traffic based on some smart routing algorithm coming from, let's say, multi-round bandwidth family, where you want to pick that particular model which is going to perform well, or which has performed well in the last time frame, last duration. So, or maybe you can also provide your own intelligent routing algorithm. Maybe if you know that during a certain time of the day, one of the models performs better compared to other models which perform better during the night time. So if you have this kind of logic coming from the business, then you can have that piece of information in a router component that we'll see shortly. And with this kind of custom logic, you can route the traffic accordingly. And the point is that the routing becomes dynamic in nature. Either the routing can come from an advanced family of intelligent algorithms, or the routing can be your custom routing as well. And then we also feel that inference graph can really help us power an AI platform. What we exactly mean is that, let's say, imagine you have a user interface. That user interface is the UI, the self-service UI for a platform. Now, you have engineers and data scientists in an organization. They simply go to that UI. They pick up components such as a data reader, a couple of ML services, a data writer, maybe a login service. Different kinds of services they pick. They simply attach them in some relationship, maybe as this example, and they want to trigger that pipeline. So behind the scene, this should go to the backend services, and it has to be deployed. It has the appropriate services has to come behind the scenes at the backend. So this relationship can be dynamically generated in some form, in the form of some configuration YAML files, some kind of configuration files, and with the help of those configuration files, we can create this system in the real time. So, and we already know if there's an AI platform in an organization, and mostly a self-serviceable AI platform, that it really saves time for the engineers, for the data scientists, because now you don't have to find all the nitties and nitties of creating stuff. You just go to that single UI, you get all the pieces that you want to connect those pieces, and simply trigger the pipeline, or maybe even schedule the pipeline. So the powering of that AI platform behind the scenes could be achieved by this inference graph. Okay, so let's go to the demo now. This is the multi-arm bandwidth, just show me.
Yeah, it's a reinforcement technology. So it's a concept from reinforcement learning. So Saurav explained, you can intelligently route it. So there are we have 3-4 models, and you know that one particular model will perform well for a particular scenario. It can be a source-based scenario, but you want it to be dynamic. You don't know exactly prior end, but based on the nature of the data, you have to choose a particular model. Then it should be intelligently routed. So there is a concept in reinforcement learning where you can do both exploration and exploitation and have a trade-off and try to switch between models as the nature of the data, as you want the output. So that's one of the concepts, and the inference graph is very powerful in implementing it. It comes in default. It's just a matter of writing up YAML file to implement anything. The basic details are already handled by sentence entries. Okay.
Yeah, let's try to now get this use case up and running. Again, we have these services with us, and the idea is that once the deployment is up, all of these services should be up and running. And if you send a request to this whole system, this ML system, then we should get the output, which should contain the 3 important pieces. One is an intent, the other is summary, and there should be an entity in the output. Okay, so I'll just try to help you understand what do we mean by graph and what is the configuration YAML file that we keep mentioning about. It's simply, so we are using Selden Core as the underlying tool to create this deployment up to help us abstract the creation of this deployment, you very well can use your choice of tool. Mostly it's available, this concept is available in other tools as well. And Serenco is an open source tool, and that is also the reason why we chose it, and it really makes our life easier when it comes to deployment. So it's abstracted over Kubernetes, so we get the best of both worlds. And then the nature of this YAML file would be, these are like technical details, but the important pieces of information is that all the running services has to be mentioned in a single place in the containers section. And
Saurav, can you increase the font a bit for people in the
Yeah.
back? Thanks.
yes, all the running services should be mentioned under the containers section. And as you can see, we have all of them listed here. These are nothing but the Docker containers. And then under the graph section of this configuration file, we mentioned the relationship as per this design, this graph. So I'll briefly help you understand what exactly it means. So if you see the first service, which is going to receive the signal, is the language detection service. So that's at the top of the graph, it's the parent. And the child of this detection service is only one, that is translation service. So that's why under the children section, there is only one children, translation. And then the translation service has three downstream services, three child services, which are intent, summary, and entity. And the output from those has to be combined, and a single output has to be created. And that's why there is a combiner component coming from this tool that we are using, Serenco. So with the combiner component, we are going to combine the output of these three downstream services into a single output. Yeah, so the output of translation is going into as input to these three downstream services, and later they will be combined using a combiner component to get a final output. Yeah, so this is the YAML file, and using standard basic Kubernetes commands, we can bring this deployment up in a single. So let's check that. Yeah, so let me delete the previous deployment.
You want to show the links?
Yeah. I'm just using the standard Kubernetes command line. Yeah. Okay, so far we don't have any pods running, at least related to services. This is one pod which is coming from the Seren tool. The responsibility of this pod or this running container is to send the deployment file to the Kubernetes cluster, and it just facilitates that YAML file and it sends it to the cluster so that the appropriate pod can be up and running. Now let's create the deployment.
Can you enlarge the font size, please?
Okay. Yeah. Yeah. So let's start with the deployment. It's just a standard basic Kubernetes command. The same deployment file that I showed you, the YAML configuration file, I'm just applying that to the cluster. So it says the graph is created. Let's check whether the pod is up or not. Yeah, the pod is running, and the containers inside the pod will take some time to come in the ready state. Meanwhile, let's also check the logs from other services. Alright, so all the other services are also up and running, and you can see the logs from these services. Okay, so I'll also have to do a port forwarding because we want to send the traffic from the browser or from the client that we are going to use. We want to send the traffic from the client to one of the ports to this Kubernetes cluster. That's why I'll have to do a port forwarding. Alright, so the port is also mapped. Right, so Now, if you go to Postman, which is a client to send the request, sorry. Yeah, so here we see there is a long text. It's a raw text that we are calling out. It has a couple of important pieces of information like dates and planet names. Yeah, so it has a couple of important pieces of information that we wish to extract out. And so we'll send this to our deployment, and our aim is to get a response which should contain all the important pieces of information. The API, of course, is local host as it is running in our system. 8000 is the port that we have mapped to the port of Kubernetes cluster. It's already running locally in my system, and this is the default API signature. If we send the request, so request is gone, and we see that the bottom three services are still waiting to get the traffic because the first the initial services are processing it, and the translation service is processing, and then once it is processed by the first two services, then the traffic parallelly goes to the bottom three services, the downstream three services, the intent, summary, and entity, and it is getting processed parallelly. Once it's done, we'll get a response back. Yeah, so it's done. All the services are done. So let me take you to the response page. Yeah, you can clearly see now that the output signal, the output contains three signals. One is for intent, coming from the intent detection model. The other is a summarized text, and the third is entity, which contains important pieces of information from that raw text. Yeah, so this is what we wanted to show you. This is actually what powers our deployment pipelines. Coming back to the presentation.
Sorry, is it trying to also smartly kind of aggregate these models, or is just running them independently but deploying them to 5 different pods? So each of the models is an
independent service. Each of the model is an independent service, so it can be developed independently. Okay, and we are just taking those independent services. We are, and in a form of some configuration file, we are maintaining the relationship between them. That your output has to go to this input, the input of this service has to go to this here. So that relationship is basically the graph that we are talking about. Otherwise, it's very well 5 independent components that can be deployed separately or can be deployed as a single unit in the form of a system.
If you want to intelligently combine, the logic can go in the combiner. Combiner is also component which we have. So say you want, today what we are doing here is just continuation of these 3 services, but if you want it to be done in a more logical way, or some logic which is dictated by the business, then that logic able can go to the combiner.
Yes.
And why would you not combine them all? Like the models are too big to be combined together.
I mean, why don't we put it in a single amalgam of model? So it's actually a basic single responsibility principle, right? We wanted to have it in 3 different cells. It's also easy to evolve. For example, when model of summary evolves, intent entity is still the same, right? So we want, it also helps us in debugging and also.
Like that's the same argument, monolith versus microservices. Exactly. So have all the models have separate service and then evolve them separately.
Okay. Sorry, go ahead.
Yeah, coming on to the value addition that this kind of design has brought to our team, our organization. So we definitely see a reduction in code complexity. Previously, we had to manage these 5 services independently. There was overhead in terms of code. Write more code to have that relationship. Write more code to route the request to the downstream services. So all of that is gone now with this framework that we're talking about. It could be very well another tool under framework, but at least we can use this concept. Then with that, we also see an ease of deployment and maintenance. Let's suppose we want to bring an additional 6th service into this entire ML system. It's very easy to integrate that. It's very easy to create that deployment containing an extra service. Or if you want to remove that extra service, also very easy to do that. Just go to the YAML file, remove it from the relationship, and you are done. Also, we see client-side API cost reduction. It was something which was an efficiency on our side from day one. Like the way services were built, one by one the services were added together. And to get the final output, the client had to make multiple API calls to each of those services. This was an inefficiency by default in our design from the day one. So finally, when we thought that now we have many services working together, with services I mean the models. Now when we have multiple services and we have to better deploy them, there has to be a standard process. So when we brought this inference graph into the picture, now there's a single endpoint that we have to expose to the outside world, and we can get the response. Yeah, so there's an API cost reduction, and with that, also one can see that the latency would also be reduced. If it's a real-time scenario, it would be really beneficial. The key takeaways, finally, what we can talk about is that we learned how to compose multiple MS services together in a form of a graph or a pipeline. We saw how to deploy that graph, how to serve a request from that graph, how standard and how easy it is once we have the services available with you. Then we also learned about the scenarios where an inference graph would be useful. I just listed a few of them. There could be very well many. And then this concept that we're discussing was not related to the particular tool that we have used. We are using Selenium, but it can very well be available from the different tools, frameworks that are available in the market. For example, the other open source tools such as Triton, there's called, in NVIDIA's Triton, there's called ensemble, and this is called scripting. And if you're using Ray in your organization, there's called deployment graph. If you're a fan of Kubeflow, it's called as MLOps graphs. I've attached the GitHub code, the code link in the slide. It's available, the code is available on the GitHub, and a couple of reference links for your information. Thank you. Any questions?
Questions? Yes. You asked last time. Can we go that side?
Hey, just one question around basically debugging of this graph. So generally we individually report the models. So
How to debug the services?
and if the inference is like, for example, say the intent is not as per the expectations, the summary also might be affected.
Yeah. So the three. Yeah, if you see the intent summary entity, there are three parallel components that are running. If one of them is not working properly, the rest of the others could still work. Okay, if one of them is not sending the output as it should have, the other signals would still be there now. Yeah, and regarding the debugging part, I think it's just the standard logs, the code logs that you can. Yeah.
Just to add, maybe it might become a bit complicated when you have a sequential service like language detection and translation, because output is combined, so now we don't know how to debug this. What we do is, of course, do it like a old school way, right? Do it piece by piece, don't take it at the same time. So we see what's the output after detection. Is it even right? Whether the detected language is right. Then only the output of detection, translation actually depends on the output of detection. Right? So we take it piece by piece.
So it's like production of if there are any issues in production by that.
So the main point when it happens in production is reproducibility, but again it will generally in our case, right, like there are millions of requests coming in our time. Right? So then first we will try to evaluate what is the impact. Say for example out of million only hundreds having this problem, then it's a lower problem to solve. Right? But say around 10% of the requests is actually having this problem, then we have enough logs that already collected to solve this problem. So that's the starting point. Now we will get logs from each and every end. So all these services independently write logs, right? So now we have full traceability, visibility. So we have dashboards available as well as Splunk where you can go through the logs. So we try to do it step by step. Generally we trace it from back. So where it's actually failing, and that's how we do it.
Hey, so so do we take care of context here and context switches from the user during the conversation?
Could you elaborate more on what you mean by context?
Like the previous messages to detect the current intent based upon the current message.
So correct, based on the session information.
So
So
yeah.
yes.
And how do we do the context switches in this case? Like when the user tries to ask questions from a completely different topic and so
I understand.
how do we detect it and change the text being sent to the intent?
Yeah, that's absolutely awesome question because we have been facing this problem. So what's our fundamental assumption is we assume the customer comes to us with a single problem, which quite often the case is not, right? So we start with the assumption that this is what is they are going to ask, and we try to detect the intent. But midway they can start. For example, in our case, right? They started with the transaction intent. Hey, what happened? But in midway they started saying, let me cancel it, right? So it's a totally two different topics, right? How do we handle? We are trying to evolve here, to be honest, but this is something we term internally as a digression. So we also are we are trying to have our model more sensitive to this, so that the model can itself detect digression. So actually we started with inquiry, but actually it's going somewhere else. So we are also trying to give that knowledge to the model, but it's a work in progress. But generally what happens is we try to make the model itself self-sufficient to understand nuances.
Okay, last question.
So I have a question, kind of slightly. So I can understand, like from system point of view, it's kind of a nice system and takes care of all those things, etc. But the question I have is like, so who uses that? Like, do data scientists kind of use them? For example, I think one of the things you mentioned, like, you just need to write an YAML file, right? I think for an engineer or for a DevOps people, like writing an YAML file is like you do that every day. But when you have to kind of do the same thing for a data scientist, it's probably not the language that they usually speak, right? And when looking at the logs, you mentioned like you just have to look at the pod logs. I think that's probably easy for the people coming from infrastructure background, but if a data scientist have to kind of understand what's going wrong, etc., how do they kind of do it? Like, I mean, is it designed for a data scientist? Like, where does that kind of fit in? How do they kind of access that?
Yeah, go ahead.
So I'm going to take this in two pieces. So first, the designing of the graph itself, right? Saurav rightly mentioned in one of the slides there is a UI which is actually backed by this in behind the scenes, but there is a UI. So here is simple. You have to just drag drop, and if you know what are the ML services you are going to serve, your ML services is already in a. It's again if you are able to do a Docker, that is all we expect from a data scientist. So the Docker file is there, it's all in UI. You have to upload the Docker file and then drag drop and create the graph. Right? Behind the scenes, it's backed by this certain deployment YAML. But for data science, it's very simple. You have to drag and drop. Now coming to the debugging part, I told it's in the form of logs, but generally the UI is more flexible, more powerful, where it's more like the logs are itself already disintegrated to units, and it's in a powerful UI. Right? We're using some tools like Looker and Splunk, where it's easy to view. So you can already see the spike in the error count, and especially what is the exact error coming up, what is the number of times error is coming up, etc. To make the conversation simple, we said we are doing logs, but how we go to the logs it's again covered by UI. So at the end of the day, it's more like UI, but engineers might log into the pods and debug. But if we have to have data science, which is often the case, right? Data scientists co-work with us to debug the tools. So often, how we interact with the data scientists is through the UI. But if there are more infrastructure level, like
So let me share my perspective. So the data scientists, since they have to build on the model, they have to improve the model. That's their primary job. And once they feel confident that the model is built, they have to hand over the model. That handing over the model is one piece. So when they hand over the model, the CI/CD kicks in. It builds that Docker image. It pushes the Docker image into some Docker artifactory. From there, if someone knows, either it be a data scientist, an engineer, or any person who has any role, just go to the UI, pick up the different components, attach them in the form of this exact graph, and just click on deploy or click on run, and it will be deployed in production. This is the basic idea, and behind the scenes, it's powered by the inference tool that we are talking about.
I can see there are a lot more questions, including I also have a few questions, but let's give them a round of applause.